Hello and greetings, class. This is specifically for Physics 1302's Section 1 at Northwest Vista College in summer 2018. Due to a mishap that I had in misunderstanding how much time I had left in the class, I will be explaining the rest of the concepts of Chapter 16 here in this video. In my defense, there's only a few left, but hopefully as I explain this, and if you're reviewing this before the exam, that it will help you answer some questions on the homework, clarify some confusions, and also help you get ready for the upcoming first exam. Okay? And without any further ado, let's get right into it. Now, as a reminder, we've been talking about capacitance and capacitors for the second half of this chapter. Let's say we have a capacitor that's connected to a battery, okay, and that it's charged, okay, to a certain potential difference, and then it has will gain charge on its plates. Say it's a parallel capacitor. As you charge it to a certain voltage, when it's fully charged, it will reach a certain potential, and the more potential you have, the more charge you have. It, so you can see, it just creates a nice linear function, and you can approximate the work done to move the charge from one plate to another, if that makes any sense. The work done moving from, there you go, for the charge from one plate to another will be equal to the change in the energy, or the energy stored rather, on the capacitor plates. And you can see it's just simply the area of this rectangle right here, or in all of these rectangles as a matter of fact. And so the base is just delta Q, the change in the charge, and the height is the potential difference across the plates. Okay? Now let's say we want to find the total area of all of these rectangles. That's the total work done on these charges moving from one plate to another. As the potential gets higher, more charge is added to the plates. So that would be equal to the area of a rectangle. This is a right triangle, but the area of a, did I say a rectangle? Triangle, rather, is 1/2 base times height. So here's the 1/2 right there, okay? And the base is actually, on the x-axis, is RQ. It's the Q value right there at the end. And the height is, well, right there, is our delta V. So this would represent the total energy stored on a capacitor, or the total work that in bringing the charges from one plate of the capacitor to another. So we can take that formula, and using the basic definition of capacitance, which is the ratio of the charge on the capacitor and by the potential difference, and I can multiply both sides by delta V. Alright, that cancels out. Okay, and then I can plug this in. I'm getting ahead of myself. Right there. And what I'm going to show in the next slide is that we can get not just one, but I can get 1, 2, 3 formulas for energy stored in a capacitor, depending on what you're given in a certain problem, like say in a homework or an exam. Whether you're given charge or potential difference, or the capacitance potential difference, or the last one. Okay, so check this out. I kind of already did the steps, so I'll just go over them again. Start with the basic formula that we just got for the total energy stored on a capacitor. Capacitor. Okay, and then using that formula that I just got, or I can write it again. Boom. Okay, let's move the Q on this side, and then this to that side, and I'm going to plug this into our formula. So now E becomes 1/2, where the Q is, now that's C delta V, delta V. So I actually have 2 delta V's, so it's 1/2, and I can put a delta V squared. Okay, so whereas we had, this is formula number 1, now I have formula number 2, as you can see right there. And then, once again, let me use green this time. I can use basic definition for capacitance, but now I'm just going to exchange capacitance and voltage to get a formula for voltage, and that will give me, yeah, that's right, Q over C. And then I'm going to plug this in there, see what I get. Just playing around with the formula, just work with me here. And I encourage you to also to try this out once you're done watching this video. Algebra is not that hard, and you can do it yourself. Take note that this exponent goes on the top and also on the bottom. So that's Q squared, C squared. One of these cancels out, and I get a final equation of Q squared, it's Q, to C. Okay, which is actually the third one right here. But wait, last one. I can actually bring this all the way back to the original equation. Okay, and but just simply by using one of the formulas that we had before. I'm going to break this down. Let's break it down. I can rewrite this as 1/2, right? And I can write this as, since it's Q squared, this is equal to Q times Q, right? Q times Q over C. But wait a minute. What is Q over C? It's 1/2 Q delta V. Boom. And it all comes back. Essentially equation number 1. This is our equation number 2. Equation number 3. They're all connected. Okay? So just take a moment. I get really excited about these things, but the reason why I show these to students is to show that they're all related to one another. And if you, my philosophy, my understanding is that if you know where these formulas came from and how they came to be, then it actually gives you more power on how to use them in a problem or an exam, or even to understand the concepts as well. Okay? Got it? Smile. And if you want, you can try this out on your own as well. You can pause or rewind. All up to you. Going on to the next slide. Okay. Now capacitors, more often than not, you will never see a capacitor that just has air in between. The air is by far the worst material you can have between the capacitor's plates, because it will easily break down and charges will fly across from one plate to another and create essentially a small version of lightning, which we call technically electrical discharge, that can actually destroy any nearby electronic components. That's something you do not want to happen. So the solution to that is to put something called a dielectric in there. Okay, it's to protect the materials, insulate. Okay, to reduce the possibility of a electrical discharge. And this should be familiar. What this does in the formula for capacitance, now recall there's another formula for capacitance for a parallel plate capacitor here. And all we do is introduce a factor. This is actually a Greek letter kappa, okay? And it's what we call the dielectric constant. And kappa is always, more often than not, greater than 1. And what does that mean, greater than 1? It means that if it's multiplied by the original capacitance right here, it always results in something that is greater, okay? So it actually increases the capacitance. That's the whole purpose of the dielectric. But how does it do that? Okay? What happens to the charge? What happens to the potential difference across the plates? Let's talk about that. I'm glad you asked. Okay. So I'm actually going to use this and connect this with the basic formula. Once again, it all comes down to basics. Formula for capacitance. Okay. So I can actually add this kappa delta V. Now, what the dielectric doesn't change is that the charge on the plates actually stays the same. Okay? But if the charge stays the same, something has to change, and the potential actually decreases. Because remember, the potential and the capacitance are inversely related. Okay? Now I'm getting ahead of myself because I do have a slide that explains that further. Lo and behold. Okay? So as you can see here, use my highlighter, this is air, and if you can see that, the voltage is a positive 2 right now. Once you apply this dielectric material in between the plates, whatever that is, I don't know, you notice that the potential went down. But what that means is that the capacitance went up, even though the potential difference went down, because they're inversely related. Okay? Simple as that. Okay? Now, what the dielectric material also does is that if another possibility is that if the charge is allowed to increase, so this is just a different case scenario. Oops. There we go. That's what I meant to highlight. If the voltage is maintained constant, then what that does, it actually can increase the amount of charge on the capacitors. Okay, but usually I think it's the previous case they said where the voltage goes down. There you go, this one. Here, where now, let me use the red, charge is constant, and then as you can see from here to here, the voltage goes down. If you look at the number of charges, they stay the same. But whether it's this case or this case where the voltage is constant, the capacitance is always increased in the presence of a dielectric in between it. Almost all capacitors that you'll see that you use in your electronic device, in the computer, that the screen that you're viewing right now has electronics that most likely has a capacitor in it. It has a dielectric in it. Okay, there you go. Diving into the dielectric material. Now, I know it says Gaussian surface in here, but I'm going to forego that. What the dielectric material does, also it provides the presence of additional molecules or atoms that also have its positive and negative. Atoms have negative electrons and positive protons, or by moving the electrons around, it creates the presence of positive and negative charges. So you see here, electric field is a vector, right? So that's how strong the electric field is, the original one. When you put the dielectric, what happened? The electric field goes smaller. And this is because the dielectric, you can see here, let me highlight this first, it polarizes the material and attracts the negative charges to the positive plate, positive charges to the negative plate. So that creates a oppositely directed electric field. You can call that negative too. And so what that does, this is the net electric field, and it makes that smaller. Okay? It reduces the electric field which is directly related to the potential, but it's inversely related to capacitance. So as the electric field goes down, the potential also goes down, but the capacitance goes up. Here we go. Okay, here's another close-up picture. I like this one from the textbook that shows how whenever you have a dielectric material in between the capacitor plates, it polarizes it. But look at where all the negative charges are pointing. They're pointing to the positive because opposites attract, and it's pointing to the positive are pointing to the negative. So that creates a electric field going the other way. Okay, this phenomena of aligning the charges is what we call induced polarization, or you can call this electric field. I forgot to put my symbol there. An induced field. There we go. Okay, we'll talk more about induction in another chapter. Okay, this picture, a series of diagrams, shows almost the same thing. This is the dielectric material before there's no electric field applied, no potential applied. Once it is, the potential is still there. But here is what I'm talking about. This is the induced field. Can you see that? There we go. And this is the net field, or the total combined field. Okay? If the original was this long, but now it's only that. But for a capacitor, that's a good thing, because if the electric field goes down, it allows more charge to be stored in the capacitor, or allows the potential to gain more potential difference between the capacitor because of the polarization, because of this polarization right there. Stumbling over my words. Okay, now there is a limit to how much potential any capacitor can take before it will start, like arcing is another term, breaks down. Something you don't want to happen, an electrical discharge. And let me reiterate that this is something bad for electronics, unless for some reason you want to destroy that electronics. And this maximum electric field that the material can take is what we call the dielectric strength. And air has by far the worst dielectric strength, as you can see in this table here. Okay? Air is actually on the top. Its dielectric constant is pretty much, for all intents and purposes, is 1. And the dielectric strength is, remember, this units of volts per meter is actually also units for electric field. So it's how much electric field it can handle. That's actually pretty much before it starts doing so. I think for your voltages at your house, you're fine. But more often than not, you'll see, there we go. Strontium titanate is a very good dielectric, makes for a strong capacitor. Rutile is also another one, which I don't know if it's on here. Water apparently is a pretty good dielectric, and as for certain car batteries, fuel cells, they are put into an electrolytic solution. So that's one way to do that. Vacuum obviously is perfect for it to arc, so that's not a really good dielectric. So capacitors, you can see here, none of these numbers are less than 1. So all this would do, except for vacuum, would increase the capacitance by a certain number. Okay? And that's why we have dielectrics inside capacitors, to prevent them, to protect them. Okay? To protect the charge that's there, because we want to release it at a certain moment in time. We'll explain later on what capacitors are used for in circuits and electronics, and what special property makes them so useful in our modern technology. Okay? I'm going to cut this video down. It's already long enough. Hope you enjoyed. Hope it clarified some things, and hope you'll use it to get ready for the exam. Ciao.